yourself. Now walk it by yourself.
Let's start with an idea that we used in the last chapter. Here's a data set. I'm going to have the yellow pigment in your skin, whether it's affected by your exam score, and we're going to have an axis out here for the zinc level that you take. Now let's be honest, I just picked this so that I could have X, Y, and Z for zinc, but that doesn't matter. The point is, let's say we have low-level zinc and high-level zinc, and here in the reflective paper, which makes it hard to see, there's a bunch of dots, and I could do regression. But that zinc level separates my data set into a low level of zinc and a high level of zinc. See how now you've got this three-dimensional axis coming out? And what we've really got are these two different regression lines. One regression line for the high zinc level and one for the low zinc level. And when we put these on top of each other, you can't necessarily see that because they're masked. Here's another way to try to explain it.
What we have here is a regression line for when zinc is low. But when zinc is high, that regression line changes to X for high. So the effect of zinc is how much this regression line twisted going from low to high.
Now, that's not any different than what we did last chapter, and instead of having two different sheets, we showed it with different colors, and that's how we got our different regression lines. For this chapter, let's imagine that the amount of zinc isn't just low or high. We actually have a continuous spectrum, an entire third dimension here, and so these dots aren't either on the board or floating, they're floating all throughout this space, and as I would walk through here, I would be swimming through the dots. Well, we can still try to model the effect of zinc on the exam scores to help predict the yellow pigment in the same way. We would have a regression line for low levels, and then that regression line would smoothly tilt and twist to represent what happens as it gets to the high levels. If our regression line had variables that don't interact, like if X was plus Z, but notice there's no multiplication there, then it would be a straight plane. And the effect of exam score would be how much it tilts this way, and the effect on the z-score is how much it tilts this way, but the paper is still flat. Just like a line would be a straight line, it's a flat piece of paper because we're working in 3 dimensions. That means that there's no interaction between them. However, if the effect of exam score changes based on zinc, that's when our paper begins to tort. And so we would use that multiplication to allow this paper to bend in funny ways to help model what happens to exam scores as the zinc increases and we're trying to predict the yellow pigment. So as you can imagine, this is a pretty real thing to have happen where the data doesn't fit in a nice flat plane. And so we want to be able to model this kind of model. Because we're not talking about categorical effects here, it's not that we get different regression lines and different regression equations. There's only one regression equation. X and Z don't turn into zeros or ones because they're not describing categories. They stay here. But what does having this multiplying effect do? Well, let's reorder our equation based off X. So I'm going to pull everything that doesn't have an X to this side. And these guys that do have an X, I'm going to factor the X out of here, so I have a 3. And here I have a 5 and a Z, so I factored the X out. Now this looks like a simple linear equation from X's view. Here's my y-intercept, and there's my slope on X. But the value of Z is changing the y-intercept, and the value of Z would change the slope. And so this Z right here is modifying the effect of X. How much does X affect Y? Well, I can't tell you unless you can tell me how much Z is. That's why sometimes an interaction is called an effect modifier. And if X is modifying Z, then Z will modify X because that twisting of the plane is going to be affecting whichever direction it is you're looking at. So you could say here, I don't know how much Z is affecting Y unless you tell me the value of X. That means if you want to explain what the effect of X is, you've got to talk about Z at the same time. And vice versa. If you want to talk about Z, you're going to have to talk about X at the same time. And so what we're going to do is talk about the effect of X at various levels of Z. So when Z is 10, X does this. When Z is 20, here's the effect of X. When Z is 30, here's how X predicts Y. And then vice versa. when x is 5, here's what z is doing, when x is 10 and 15. And so we're going to pick some levels to help explain what's happening at the z and x values. And then when we're done, we'll be able to have a couple sentences. Here's, in general, what the effect of x and z are doing. In other words, we have some twisted picture, and if you just look at the xy shadow, you don't really see what's going on here. The way that you want to be able to see it is we're going to take some slices, and we're going to cut this in sections and say, now that you are looking at a slice of what's happening, you can piece together, oh, you can either in your head build that 3D model, or you can just say, I see what the effect of increasing zinc is, and I can see what the effect of increasing the X for exam score, right? So as the exam score increases, well, it depends on the zinc level. And here I can kind of see that relationship. Now, when I showed you that shadow before, that's not a lot of clues that there is this 3D warping going on. So in the next video, let's talk about what clues you are supposed to spot as a statistician to say, yes, there's an interaction here, and I know how to slice it to find it and get it.